Any arbitrary vector in the xy plane can be broken down into two vector components, one lying along each axis, that add vectorially to equal the original vector. Take for example an arbitrary vector A. It can be expressed in terms of its x and y components, a sub x and a sub y, that lie along the x and y directions respectively. The two components are drawn parallel to the x and y axes, and are therefore perpendicular. They add vectorially to equal the original vector A. In other words, vector A is equal to vector A sub x plus vector A sub y. Another convenient way to express a vector in terms of its components is to draw the components along each of the axes as shown in the figure. This is completely equivalent to the previous representation. The slight disadvantage to drawing the vector components this way is that we lose the tail-to-head arrangement of a sub x and a sub y, which is a nice reminder that they add vectorially to equal the original vector A. The following definition summarizes the components of a vector. In two dimensions, the vector components of a vector A are two perpendicular vectors a sub x and a sub y that are parallel to the x and y axes, respectively, and add together vectorially such that the vector A equals vector a sub x plus vector a sub y. We should point out that the vector components of a vector depend on the orientation of the axes used as a reference. In other words, they depend on your choice of the coordinate system, which is arbitrary. In some problems we encounter, it will be more convenient to rotate our xy coordinate system, such as in the figure. But notice we can still break an arbitrary vector down into its component vectors that lie along the axes of our coordinate system. While the components of a vector are vectors themselves, it is often useful to work with scalar components, which are positive or negative numbers with units, and are defined in the following way. The scalar component a sub x has a magnitude equal to that of vector a sub x, and is given a positive sign if vector a sub x points along the positive x direction, and a negative sign if vector a sub x points along the negative x-axis. The scalar component a sub y is defined in a similar manner. Consider the following vector that lies in the fourth quadrant. The following table shows the distinction between the vector and scalar components of vector A. Notice that because the y component of vector A lies along the negative y direction, its scalar y component is negative. Another method of expressing vector components is to use unit vectors. A unit vector is a vector that has a magnitude of 1 but no dimensions. We will use a caret symbol, often pronounced hat, to distinguish it from other vectors. Thus, the unit vector x hat points along the positive x direction, and the unit vector y hat points along the positive y direction. The scalar component of a vector along a particular axis direction, written along with the unit vector along the same direction, is equivalent to the vector component along that direction. For example, for an arbitrary vector A, the vector component along the x direction would be written as a sub x times the unit vector x hat, and the vector component along the y direction would be written as a sub y times the unit vector y hat. The vector A can be written as a sub x times x hat plus a sub y times y hat. If we know the magnitude and direction that an arbitrary vector points, then we can resolve or break the vector down into its x and y components. This will be an important technique in adding multiple vectors, as we will see in the next section. For now, let's illustrate the resolving process. Consider a vector A of magnitude 125 meters directed at 50 degrees above the positive x-axis. Find the x and y components of this vector. We can resolve the vector A into an x and y vector component that point along an axis direction. Notice that the two vector components are perpendicular to each other and add vectorially to equal the original vector A. From the figure we see that the two vector components form the legs of a right triangle, and the original vector A is the hypotenuse. Since we know the magnitude of A and one of the angles in the right triangle, we can use the trigonometric functions to find the magnitudes or lengths of a sub x and a sub y. Notice that a sub x is the adjacent side to the known angle, so we can use the cosine function. The cosine of 50 degrees is equal to the adjacent side a sub x divided by the hypotenuse a. Thus, a sub x will be equal to a times the cosine of 50 degrees, which is 125 meters times cosine 50, or 80.3 meters. The y component a sub y is the opposite side of our known angle in the triangle, so here we can use the sine function, which is equal to the opposite side a sub y divided by the hypotenuse a. Thus, a sub y will be equal to a times sine 50 degrees, which is 125 meters times sine 50, or 95.8 meters. Since the components a sub x and a sub y and the original vector a form a right triangle, we can use the Pythagorean theorem to verify the magnitude of a is indeed 125 meters. Using the Pythagorean theorem, we have a squared is equal to a sub x squared plus a sub y squared, or a squared is equal to 80.3 meters squared plus 95.8 meters squared. Solving for the magnitude of a, we calculate a value of 125 meters, in agreement with the original value. Two more important notes in this section. First, for a vector to be equal to 0, every vector component of the vector must be equal to 0, which means every scalar component must be equal to 0. For example, if a two-dimensional vector A is equal to 0, then the vector components vector a sub x and vector a sub y must be equal to 0, and the scalar components a sub x and a sub y must also be equal to 0. Second, if two vectors are equal, then the vector components of each must be equal and the scalar components of each must be equal. For example, vector A will be equal to vector b if and only if vector a sub x is equal to vector b sub x, and the scalar components a sub x and a sub y are equal to the scalar components b sub x and b sub y respectively. Now that we have seen how to resolve a vector into its components, let's see how we can use this to add vectors.